Okay, so as I mentioned before, we are going to do today stochastic differential equations. This is going to be the 10th lecture. And again, so first off, before we go into that, we're going to look at the deterministic versions. So we're going to look at the deterministic differential equations. If I say deterministic, I basically mean that there is no stochastic component involved. Okay, I will use the abbreviation DDA for hereafter. So if I say DDA, I mean deterministic differential equation. I'm only considering the linear ones, and then we're going to have their stochastic counterpart. Now, if I say stochastic differential equation, there is always going to be a stochastic process involved, which is actually, on the other hand, evolves around a certain Wiener process. So usually there is going to be a Wiener process which is going to be there. And SD is basically the abbreviation that I use hereafter. So if you see SD, this means stochastic differential equation. And if you see DD, it means deterministic counterpart. Now, then of course, I'm going to show you how to solve them. So basically, it's not about the differential equations, it's about solving them. And both deterministic ones as well as the stochastic ones, but understanding the solution of the stochastic ones, you would need to understand basically the deterministic ones, which is not difficult. And then you're going to see the moments, and basically for both the first and the second moment. So then using basically those two, you can put together the variance of the processes. So this is basically the way that you would address it. Okay, so you would establish the dynamics of an acid, for example. Then you solve the stochastic differential equation, and after that you would basically use the moments, basically establishing the mean and the variance, and that's pretty much it. Okay, you're going to see some examples. So this is going to be based on Ito's lemma. So if you understood last lecture, you will going to understand this one. It's not just basically nothing new. So I'm going to put those things together, and that's going to be it. Fubini is going to be there, and that's pretty much it. Okay, but Ito's lemma is going to be important. Now, I'm going to start with the deterministic ones. Okay, deterministic ones is basically the linear ones, and I'm only considering linear ones of some sort. Okay, but I'm trying to put that basically in more general perspective. Now, there is two types. The first type I call homogeneous, and the other one is going to be inhomogeneous. Okay, so in basically written as a differential, the homogeneous version of a deterministic one. Again, X is not a process this time, but it could be. So it could be a deterministic process if you like. Okay, so for example, you have like constant growth with a constant growth rate, something like that. All right. So I'm going to basically address that one. There is going to be a deterministic function involved, CT, but that's not basically what we're trying to establish. And then you have basically, this structure. Okay, so that is basically a differential equation. And it's deterministic because there is no processes involved, no stochastic processes involved. Okay, you understand the point? All right. Now I'm going to show you how to solve these, and this is basically what the exercise is predominantly, this lecture is going to be about. And addressing in case of stochastic processes, I'm going to address the moments as well. Okay. Now, first off, before I address this, I'm going to basically create a differential, and for that I'm going to use a function, and the function is going to be the logarithm. So this time it's going to be the logarithm, just to show you how to solve this equation. Okay, you can take the result as basically, given. So when you see the equation which solves that, you can use that and basically take it into exam. You will not need to show it again. Okay, so nothing will basically what you see where you need to show something which is required to use is going to be basically just addressed here. Okay, so you can take that into the exam. Okay, now the function that I'm going to use is basically addressing the dynamics. You can call it the deterministic process, which again, if let's say this is a constant, then you have basically constant growth rate. So that will be basically the growth rate. But I'm going to show you that one later on. Anyways, so I'm going to basically address it by its derivative. Okay, so again, assume that the functions that are involved are going to be differentiable almost everywhere and continuously differentiable almost everywhere, so such that basically corresponding integrals exist. So basically those things need to exist. Again, I'm going to use differential. Okay, so if you can take that basically for when you're familiar with basically basic algebra. So when you have basically the first derivative of a function is, according to the Leibniz notation, basically a differential of f divided by the differential of x. So this can be also expressed by the differential of f is going to be the derivative of the function, whereas basically you have a differential attached to it. So that's basically something we should be understanding. Okay, and I'm going to assume that the functions that are involved, so I'm not going to say this, are going to be basically continuously differentiable almost everywhere, mostly basically on a closed and bounded interval that goes from 0 to t. Okay, so you don't have any stochastics involved, but I'm going to generalize that for stochastic processes, especially for diffusions. So then you'll have basically some specific functions there. All right, now basically coming back to that, so you'll look at basically the increments of the logarithm, which is basically as you would address the return. Okay, so you look at basically, if let's say an asset evolves like this, it could be maybe the risk-free asset or something where there's no stochastics involved. You would address basically how the relative change of the asset price is by addressing the differential of the logarithm of the function, all right, that you're looking for. So you want to basically find x here. Okay, so that's the goal, right? Okay, so I forgot to say this, but you're going to see how this works. Okay, and then you can use that later on. Now, creating that requires basically differentiating the function. Everybody knows, I assume. Okay, just for the record, for the exam, you need to be familiar with, basic differential calculus. I think that should be fine. So, first derivative and stuff like that, all right? Now, if the function is a logarithm, then its first derivative is going to be 1 by x, of course, if you differentiate the logarithm with respect to x, right? Okay, so you're going to get 1 by actually the function that I'm looking for. So this time around, x is a function that I'm looking for, and that is going to be actually, you have that here, not multiplied, but this is basically, a pseudo multiplication that you have here. It's not a real multiplication, but the differential of the function is here, so that you can put it basically down there. That's it, okay, which I do, and that is a function itself, right? So at least includes some function itself, and this is basically it. Now, as you see, okay, you have x in the denominator as well as in the numerator, actually, so that goes away, and then of course you have basically just c time. Just c versus basically where the differential time involved. Okay, so this is basically the change. All right, so this is c is a deterministic function in this regard. If it's a constant, then you have basically a constant return or a constant growth rate would be basically evolving some sort of risk-free asset, but it could be deterministic. Even if it's not a constant, it could be a deterministic one. Okay, so that's basically what you have here. Now, but you still don't have the solution. So if you want to get the solution, you need to basically reverse the logarithm. And you can do this basically by using the exponential function later on. But I'm going to show you how to. So what I'm going to do now is I'm going to integrate the function. So I'm going to integrate both sides. I'm going to integrate that one and that one. Of course, you don't have that anymore. All right, so I'm going to basically integrate the deterministic function. And for doing so, to be more consistent, I'm going to change the integrator to s. Okay, so that goes from 0 to t, because I'm going to basically always, okay, so in this regard, without loss of generality, always, and I think I'm going to take this into the exam as well, to make that possibility that, because when we look at stochastic processes, I'm going to basically address those things on that interval. Anyway, okay, now if you integrate the left-hand side, you would need to integrate the right-hand side of the equation as well, and you do this with respect to s, of course, but I would need to change basically the argument of the function, because I cannot call it t. So you can call it anyhow, you can call it x, whatever you like, or at least not capital X, but it's not supposed to be basically equal to the upper end point of the interval. all right, on which you're basically integrating it. And since the function, again, so I'm not going to say this because I was not very technical, at least in this, on this chapter regarding it, okay, but since, I mean, for that integral to exist, the function c would need to be basically continuously differentiable almost everywhere, right? I mean, we were addressing it, so that's just, you know, a Riemann integral that needs to be basically existing. All right. Now this is still not basically solving the differential equation, but what you do have is basically the upper endpoint at the logarithm of x minus the lower endpoint. Okay, because you're basically just technically you're summing up the increments of the function. So that basically reversing it, right? This is just basically a simple reverse, and we were talking about it. Okay, and now what I'm going to do now is basically put on the starting value or the logarithm of starting value to the right hand side of the equation, and now you would need to reverse the logarithm. So what you have is the logarithm of the process, but not the process itself. Okay, I'm calling it process, so you can call it deterministic process. In order to do so, you could simply reverse it by the exponential function. So exp means e to the power of, whereas e is the Euler's number, of course. And then you have basically the starting value. Now, what you do have in that regard, so you have, this is the exponent, right? And if you add something in the exponent, right? So you have basically, for example, a to the power of m times a to the power of n, which is a to the power of m plus n. So you have basically a sum here inside the exponent, which is there. Then you would need to multiply the corresponding powers to do so, okay? So that changes. If you multiply two powers for which the base is the same, then you would need to add the exponents, and that's exactly what is happening here. So if you want to split that, this is e to the power of the integral times e to the power of the logarithm of the starting value, which is basically actually the starting value itself, because e to the power of the logarithm of the starting value is going to be the starting value. So that's basically what it is. Okay, let me check. It should work, okay, but I'm not sure. Last time it didn't, but because I was messing up, but now it does. All right, okay. Is this understandable now? Okay, so this is basically how it is, and that's a solution to this differential equation, by the way. It's a deterministic one, so this is the way to solving it. All right, okay. Now later on, I'm going to do the same thing, whereas you're going to have a stochastic component in it. And then, of course, this changes some things, but not that much regarding, basically, I mean, due to the fact that there is going to be a Wiener process, I'm going to make that basically on diffusions. So since you're going to see a Wiener process, and since that has a quadratic variation, which is finite, you're going to have an additional term related to its diffusion anyway, okay? And that is a solution. So this is basically just asking you to do it. Now, if I give you c, which is a function, then you would need to integrate that. If it's a constant, for example, then you could basically just, you know, solving it. So for example, if it's a constant, then you have e to the power of, I mean, that would be just c times whatever. Okay, so t, that is it. Okay, you would basically differentiate it with respect to s also. Anyway, so that's going to be, I mean, okay, I'm not going to finish that one, but this is just basically the issue here. Okay, so, and that's basically summarizing it here. So that is in the first part. Okay, this is simplest form. I'm going to basically defining another function which is actually yielding the solution. So z at point t is the solution times the starting value, of course, okay, which is there. And the reason for that is because, again, I'm going to generalize it to a non-homogeneous differential equation. So you're going to have some additive constant in there into that function. So I'm talking about that one. And that blows up a little, you know, this expression. So I'm going to basically just compare it to it. But is this understandable so far? Okay. Now I'm going to look at basically the second part, whereas you're going to see an inhomogeneous or a non-homogeneous one, but it's going to be still a linear one. And I'm going to talk about linear ones only, at least in this part. Okay. So I'm going to have two functions now to be basically the drift function. One is c1 and the other is going to be c2. And as you see, c1 is the multiplicative function which is a deterministic one, of course. That's going to stay deterministic even if X will be a stochastic process later on. Okay, but I don't want to mess it up with the notation, so this is just basically what you end up with. And C2 is the additive function, and this is all part of the drift. Okay, now the solution will change. Okay, so and it's going to be a little bit bigger, a little bit again, so might be feel, you know, it's kind of too harsh, but it's not that bad. Okay, so this is just how you're extending it, and that is going to change the C1, and that's it. Okay, and I wanted to basically to have some commonalities here, so both the inhomogeneous as well as the homogeneous version kind of resemble to each other. The only difference is basically that you have something in this parentheses, an additional integral which you would need to solve. So this additive constant changes, unfortunately. It changes a lot, but you'll see some examples. Okay, I'm going to prove this, don't worry. Okay, so you can take that into the exam. Okay, so you can take that, and there is also an exercise, so you can basically just check it out, for which basically you have constants. So what happens if you don't have basically deterministic functions as the multiplicative and the additive component, as basically what you have constants then? Okay, now if you have constants, which is a corollary to the previous lemma, of course, where you had the functions, then you could basically address this integral right away. The antiderivative of this function, right? I mean, again, so you have that basically inside basically the, as the exponent, so e to the power of, right? Now, the antiderivative is going to be C1 times S. That's basically the integral, and this goes from 0 to t, and that's basically it, all right? Or inside there. So, sorry, that was wrong. That was wrong. C1 times S, and inside, right, as the exponent. So not outside, inside the exponent. You go from 0 to t. This is it, okay? So not basically outside of it, inside of it. Sorry, I was wrong. Okay, if you do, then you got basically C1 times t, right? Because if you take the derivative of that with respect to t, you're going to get C1 back, which is a constant. And then minus the other one, which is the antiderivative at point 0. Now, the antiderivative at point 0 is going to be 0, so you have basically left with e to the power of C1 times t, and that's it. So that is basically just this function now. All right? And as well as that one. Z at point S is going to become e to the power of C1 times S. All right? So if you change the argument from t to S. I'm going to calculate this integral, and keep that in mind because I'm going to use that one quite frequently. This goes from 0 to t, of course. Now, C2 is a constant, so that's not going to change. All right, it's not going to be a function anymore. And I'm going to take that, so write it differently because I don't have much space. So the reason why I was writing it like this is because I was too lazy to create some space. This is e to the power of negative, because it's in the denominator, negative C1 times S. This is basically the antiderivative of that function. How come? Again, if you're not sure, this is C2 by e to the power of C1 times S. Okay? And that is basically equating to e to the power of negative C1 times S. You see? Okay? Because, probably you're familiar with basic exponentiation, so a to the power of minus m equals 1 by a to the power of m, of course, right? Okay, so you just see that. All right, so I can write it like this. Actually, okay, this is not the antiderivative. I was wrong, sorry, for expressing this. I wanted to get the antiderivative. That's what I had to say. I was rewriting it first, and then you're going to get it. All right, with respect to s, of course. This is not the antiderivative. I was confused. So I wanted to get the antiderivative of that, but I was just rewriting this expression so you see how this evolves. Anyway, all right, so let me continue, and then basically I would like you to ask you to keep that in mind because this is an expression that I use quite frequently, but I only solve it once, so basically I would like you to ask you to pay attention to it. All right, now let me just basically address the antiderivative of that. Maybe if I'm rewriting it a little bit more efficiently, so C2 times e to the power of negative C1 times S, and I'm going to look for the antiderivative with respect to s, of course, right? Okay, C2 is a constant, so that doesn't disappear. Okay, but if you, you would differentiate that with respect to the chain rule, you would find that basically the inner derivative would be negative C1. Okay, so if you kind of reverse it by a constant, so you add times negative 1 by C1 to it, that's basically the antiderivative of that. So you're going to see this down there, so you have negative C2 by C1, okay, and then you have times e to the power of negative C1 times s. Now, I was already plugging it in here, so if I would just basically allow me to just basically address this one. This, if I would continue, but I didn't because I needed more space. The function that you see here is one antiderivative of this function, all right? If you differentiate that function with respect to s, you're going to see it again. Okay, so that's the reason basically why it's an antiderivative. And because based on the chain rule, you got the constant, which is negative C2 by C1, times the other derivative, which is e to the power of negative C1 times s, times the inner derivative, which is negative C1. And so since you got C1 inside here, this is going to cancel out. So, and since it's negative, the negative sign. So you're going to get this back if you differentiate that function below. Now, if you put in t, which is the upper endpoint, you're going to get t. All right, so e to the power of negative C1 times t times the constant is going to be actually the function at the upper endpoint. And then minus 1 is going to be basically the result for the other. Because how come? Because if you take the lower endpoint and put it in here, you got e to the power of 0, and e to the power of 0 is going to be equal to 1. So that will be basically the lower endpoint, or the antiderivative at point 0, which is there. All right? And then you would still need to multiply that by the constant, by the way. Okay, so then I'm done. Okay, so this is it. This is it. This is equal to this integral. And I'm going to replace it by it. So this is what you're going to see. All right? Okay, you see that there. And then I'm going to rewrite this so you see it up there here at the top. So this is an exercise that I would like you to basically just to do it also. This is, I think, exercise 9.2. Spent last night doing that, so check it out. And just use your previous result, and that is going to be, this is the solution of this differential equation. All right? Okay, so when you have a linear trend, actually you have a linear, it's called linear because you have a linear trend, all right, regarding the increments of the process. All right? A linear trend for the increments, and that is basically how it evolves. All right, yeah, okay. Now, next, I'm going to basically, show you that one. So I wanted to basically prove that previous statement, whereas you had the big one. Okay, now, based on a quotient rule, I'm going to basically do the following. So I'm going to basically address the differential of the quotient, which is not differentiating the quotient. It might not even be the case. Okay, so who knows basically whether the function is going to be differentiable or not. Okay, but I could basically address this differential still, because it could be integrable, and to be basically for the function to be integrable, it's not a strong requirement. All right. Anyways, okay, so based on it, I'm not sure if you're familiar with the quotient rule of differentiation. So u times v, of course, and you might differentiate that equals u times v minus u times v prime, and then divided by v squared, right? Okay, so that's a quotient rule, but I'm going to express this in terms of differentials. It's not difficult. You take the function z, okay, which is the numerator, and then you take the differential of the denominator is the red one. And then you take the differential of the numerator, and then you have minus the other way around. Minus the numerator, and then you take the differential of the denominator. Just as, basically kind of reversing it, but it basically matters what you're differentiating. And down there in the denominator, you're going to get the square of the denominator, which, the previous one, which is z. So z squared is going to be basically the denominator of that differential. You understand this, guys? Okay? So when you would basically integrate that, okay, then differentials would disappear. I mean, that's basically what it would be. All right? So then you have basically what it will end up with. I mean, okay, that's just basically what you'll have. Anyways, okay, now I'm going to use those expressions. So let's extend this a little bit. I'm just going to plug it in, okay? And then I'm going to clean it up a little bit. So you have those z's around, which is basically having it actually in denominator, you have it twice. But here is a sum. So when you basically cancel expressions from the sum, you need to make sure that every summand has the same factor, which is z. So take it out, okay? Clean it up, succeed it better. Again, it's not difficult at all, but you see basically there is too many indices and all that stuff. So I take it off from that fraction, and what I also see is that those two are equal, and they are basically going to be subtracted from each other, although there is a differential to each attached to it, but it doesn't really matter, so you can simply just ignore it, okay, which I do. This is just a pseudo multiplication, by the way. And then you're left with just this expression, and that is a humane, let's say, expression, so that's not looking that bad, you see, okay? This is, let's suppose it's going to be integrable, okay, which I need to make that assumption. So I will integrate on both sides. Why? To get rid of the differential operator, you see? You can reverse it. You saw that on a previous section. You can reverse it, but basically integrating on both sides. So that's what I did. Integrating on both sides, then this differential operator disappears. Then you have the integral on the right-hand side and the starting value, because this expression minus the starting value was the integral of the differential of basically of the quotient. All right, so that's basically what it was. So let me remind you, the integral of the differential, okay, of the quotient, which I called x, so I'm simply just calling x, and then you had, what was that? Then you had z, okay, so which is basically the integral, and then you would take that from 0 to t. It just, again, so it's not a big deal, okay? So this is going to be basically, I mean, let me prepare those fractions. So you have x at point t divided by a z at point t, which I'm going to address, minus x at point 0 divided by z at point 0. So this is basically how you end up with, okay? And I'm going to use that quite frequently, so I hope you understand the point. Again, yes, you got a question?
Just with regards to intuition, is there any about xt over zt and the differential? Can I?
Yes, that was that. So if you integrate, I mean, I was basically addressing it differently. So within the discrete case, okay, if you sum up the increments of a process, right, you're going to get back basically, let's say, from the first, so, I mean, from the, you got basically these increments from time point t, so from 0 to whatever, okay, so that was, okay, I was using s, all right, so let me use s here, so those t. You're going to get basically xt minus x0 back, right? Sum up basically the increments. We were talking about that. Now, in terms of basically continuous case, you have the integral with respect to, actually, basically, this is a Seychus integral. So you have the function here, right? So this is basically how it works. And let's say the integrator is s, or actually g, which is basically the integrator. Now, if the function satisfies certain conditions, right, which we talked about, this is just going to be actually equal to the function. I mean, it depends basically where you're integrating at. So I assume basically from 0 to t, this is going to be the function at point g minus the function at point 0, okay? Because this is basically how this works. And that's exactly the same thing that I did, okay? So that's exactly what you see here, because the differentials were disappearing, okay? The quotient as a whole, so you cannot split it, divide, I mean, basically at point t minus the quotient at point 0, which is it, okay? So if you define that to be a function. You understand? Okay? So you're going to, I mean, last time I was showing you how to go from the differential notation to the integral notation and vice versa. So I wanted you basically to check that out, because I was addressing Ito's lemma, for example, both ways. using differential notation as well as the integral notation, by the way. All right? Okay, so I'm integrating from 0 to t, and then of course I would need to change the integrator to s. And that's it, because again, keep in mind, I'm not sure if you're seeing that, but z at point 0, what is that? Okay, now, z at point 0, you would need to replace, I mean, you can do it over here. The integral from 0 to 0 is always 0. Okay, so then you got e to the power of 0, and e to the power of 0 is going to be equal to 1, of course, right? So this is basically going to be equal to 1. So at the starting value, so I'm talking about this expression, which is equal to 1 now. So if this is equal to 1, so that denominator is equal to 1, then you can take it out, which I did, and that's it. And then if you solve this for xt, all you would need to do is just to multiply by z. That's it, both sides. So you multiply the starting value, I'm calling this starting value, the starting value basically of x, and the integral, both you multiply by z, and that's going to be the solution to that equation, okay? So that's basically it, okay? You're done. Again, because solving this equation for x is not a big issue, okay? Does that make sense to you guys? So this is how you do it, okay? Is that all right? Okay, I hope at least. Anyways, okay, so long story short, now I'm going to address basically the constant version. Check it out. So I'm going to do this exercise now, where basically both the multiplicative as well as the additive functions are constants now, okay? So no dependency on basically on any argument. So you have basically a constant over here. Now, first off, I'm addressing again this expression, which is e to the, I mean, I was already doing that, so I'm just basically recalling it. That was e to the power of c1 times t, which I had done, right? You see? And I'm taking that and I'm going to put it in here, okay? And here, of course, right? So that's basically what you end up with, okay? And this is it, okay? So here it is. This is the integral that I'm looking for now, and I was addressing that already, guys. So I'm not going to do it again, but I was replacing it. So you can check this out. Starting value, and now minus, how come? Because the antiderivative of that function, maybe you remember, was negative c2 by c1 times e to the power of negative c1 times s with respect to s. And s goes from 0 to t. So negative c2 by c1 times e to the power of negative c1 times t. And then minus 1, because this is corresponding to the value of the lower endpoint of at least the exponential function, okay, which is multiplied by a constant after all, okay? And this is it, guys. This is the solution, as you see. No, this needs to be multiplied by z. But if you multiply basically the expression, which is framed now in the pink frame, by z, you're going to get the solution of the equation. And that's it, okay, which I haven't. So I was not finalizing that one, but it's not what was basically was difficult. All right, now, this time around, and this is going to be the second part, I'm going to look at solutions of their stochastic versions. And regarding their stochastic versions, so SDE, right, means stochastic differential equation. I'm going to basically evolve around the Wiener process, but not just the Wiener process. Actually, it's going to be diffusion, but first off, I'm going to do that. So there is going to be a homogeneous version, and there is going to be an inhomogeneous version. First off, I'm going to look at the homogeneous version of the linear stochastic differential equation. Okay, so that's going to look like this. Check it out. Okay, so for a homogeneous version, what does that mean? This means that you only have multiplicative functions, but no additive functions yet. Okay, I'm starting by basically by the multiplicative versions because it's much easier. Again, this is not particularly difficult, guys. So I'm saying this to be honest. I'm not basically, if a lecturer says it's not difficult and you feel like kind of frustrated because you're not basically, you know, you're not understanding it, and then so you feel kind of dumb And I don't want to basically talk you down. I just basically give you the motivation that after all, it's not that difficult. So I have to admit it looks horrible. And when I saw this at the beginning, I was also very confused. But the confusion is always coming from these indices and all that stuff. So not really basically from the expressions actually. Anyways, now the difference basically, the stochastic and to its deterministic counterpart is that you also have a diffusion. Okay, so you have a diffusion. This is the diffusion function. All right? Whereas for the deterministic one, you only had the deterministic function at the beginning. Now, if typically it's a Wiener process because, for example, in finance, that's the most common process that you're going to use. And I'm going to basically just present the solution first, and then I'm going to show it to you. It's going to be basically, a little painful, I have to admit. Okay, so it's going to be painful, but after all, when I help you break it down, it's not that bad. So now I'm going to define a function z, which is multiplied by the starting value again. So it kind of have the same structure as the deterministic one. The only difference is the function z, which is capital Z now. Again, that has a reason because it's going to be a stochastic process. All right, so I was basically, using that one. Okay, so z is going to be a stochastic process itself. And this is going to be e to the power of, and again, don't be scared. It's not that bad. It comes from Ito's lemma, guys. Okay, so you go from 0 to t, as far as the integral is concerned. You have the multiplicative function, and then minus 1/2 times g squared, and g is basically the multiplicative function of the diffusion. Okay, you can call it volatility if you like. So this is basically, some sort of volatility of the function. All right, and again, but I don't really like it. But again, it has to do something with the returns, and that's basically it. Okay, and then of course you have also the stochastic part, which comes after. And so this is what it's going to be. Now, the only difference basically to the deterministic part is that you have a stochastic integral, right, which can be addressed. This is a stochastic Riemann-Stieltjes integral. And then you have the additional term, negative 1/2 times the square of that expression. And that comes from the fact that the Wiener process has a quadratic variation, which is non-zero but finite. Okay, so this is where it's basically coming from. Because when you address the same thing, and again, so this is also part of an exercise. Again, it looks horrible, but the inhomogeneous part, the inhomogeneous counterpart, where you also have additive functions, not just multiplicative ones, but additive ones in both the drift as well as the diffusion function. And I'm going to call in basically in contradiction to the book, C1s and C2 to be the functions of the drift, and then G's, okay, G1 and G2 are going to be the functions of the diffusion, you see? All right, now, basically the functions with the index 1 are going to be the multiplicative ones, and the functions with the index 2 is going to be actually the additive ones. All right, now, then of course the solution would change. So of course I'm going to change the actually those expressions here, which you see. All right, so those are the expressions that I change first. Okay, so C1, these are actually all of them without any exception still the multiplicative ones. So that doesn't change actually. That function didn't change. Okay, if you go from the homogeneous to the non-homogeneous version. But, well, this is not nice, I have to admit. So there is going to be an integral, which is also multiplied by z. You have basically the function z2, which is the, C2, which is the additive function of the drift. Then you have minus the multiplicative function of the diffusion, okay? Diffusion function, you can say. Then the times the additive function divided by the square of, divided by z, not the square, by z. Z is here. Okay, so that function must be found first, okay? It's just not it's not easy, I have to admit, but again, it is what it is. And yeah, and then of course you're still not done, because you have also some stochastic integral involved. Begin for the Wiener process. So the Riemann-Stieltjes integral, which can be also further, recalculated by why would I? Okay, so why would I? I would not need to do it. Okay, it looks horrible, I have to admit, but I'm going to prove it still. So it's not going to be that big of a deal. Check it out. First time I'm going to go back to the homogeneous version. That's easier to prove. Okay, and I'm going to take basically the proof on the second one, building around that. So that's what we're going to do. Regarding the homogeneous version, you need to have Ito's lemma. And this is basically applied on the differential of the logarithm. Or you can say the increments of the logarithm of the process. So xt is a process. Now, just for the record, guys, if c and g are constants, okay, as you saw, then this function is a geometric Brownian motion. I'm not sure if you're recognizing it. Okay? Anyways, I'm going to apply basically the Ito's lemma on the logarithm of that, just as basically the case for the Black-Scholes model. You saw basically Ito's lemma last time, so I'm basically just repeating myself, but that's basically the formula that I'm going to use for diffusions. So x is the diffusion here, and f is the logarithm. Now, of course, you would need to have its first derivative, and you need to have its second derivative. So if f is the logarithm, then its first derivative is going to be 1 by x, if x is basically the argument. And the second derivative is going to be negative 1, x to the power of minus 1 is going to be negative 2 times 1 by x2. That's it. All right? No, negative 1/2. There we go. So it's it. Yeah, this is it, I hope, at least. All right, okay, so you're going to see it then. Anyways, okay, so 1 by x, you see it here, okay? So I'm going to basically applying Ito's lemma. And then you have plus 1/2 times 1 by x squared times t, right? Okay, so you'll see basically, I mean, this is it. And then that's it. So then you have basically the square of g, and there you go. Okay, so this is basically how you're doing it. Okay, all right. Again, let me recall. Basically, if the function is a logarithm, its first derivative, which is basically x to the power of minus 1, its second derivative is going to be negative x to the power of negative 2. All right, which is negative 1 by x squared. That was it. All right, I got it right. Yes, so this is the reason why the sign had changed here. Okay, because the second derivative actually has the minus 1 as a factor. So I was already changing that. Okay, and then you have the square of the diffusion, and the diffusion is here. So this is going to be its square. You see? Okay, so that's something you should need to have, basically, and you need to understand that. Okay? And then, of course, you have dt, which is the differential attached to it. Anyways, okay? Is that clear, guys? Okay, so that was it. So this is basically why negative 1/2 is going to be there, right? Okay, now I'm going to replace the differential of the process, which I'm basically trying to address, by the geometric Brownian motion by itself. Okay, so that's basically how you do it, which I did. And then I'm going to clean up down there. X squared in both the numerator as well as the denominator cancels itself. So it will basically eliminates itself, and then you just have negative 1 times g squared. Now g squared again is the multiplicative function of the diffusion. Okay, and that looks quite relaxed now. I'm also eliminating x, the x's. Okay, so you're going to see them as well in both numerators as well as the denominator. So I'm taking that out. And since it's a sum, it needs to be in both, right? So, I mean, it's not very precise because people are kind of struggling with that. But since there is a sum, it needs to be in both. And yeah, so here it is. And then, of course, it looks much better now. So then I'm basically, since you have dt here as a differential, I'm going to take minus 1/2 times the square of g inside that differential. So this is basically what you end up with. That looks familiar. And then if you integrate that, which I did, so check it out. First, I was basically just writing it down. This is how you integrate it, so you can basically just keep that in mind when you do it. If you integrate it, of course, you're eliminating the differential operator, but you need to understand that you would need to integrate what's on the right-hand side with a new integrator, okay, so which I will call S, and then you integrate that from 0 to t, and then of course you're not supposed to forget the starting value either, which is also on the right-hand side. So if you remember that structure, okay, how you go from the differential notation to the integral notation, and we were doing this also last week, then this is just basically consequential, all right? So I'm basically just doing the same thing over and over again, okay? And again, but I have to admit, it's not very accessible at the beginning, but it's not that difficult if you think about it. I'll try to present it using these colors so you're not going to get too confused by that. Okay, now, if you want to isolate x, you would need to reverse the logarithm. And the logarithm can be basically reversed by its inverse function, which is the exponential function. So e to the power of the whole thing, guys, the whole thing, right, is going to just reversing it. Now, e to the power of the logarithm of the starting value is going to be the starting value itself. So that isolates basically the starting value as it is. But then times actually the exponential function or basically the whole thing, okay, as the exponent, guys. Okay, so that's why basically I like that notation, because I can pack the exponents whatever I like to, okay? It doesn't really matter. And that's it. This is it. This is the solution, right? As you see. Okay, so this one for the homogeneous one. All right, so in case of the homogeneous one. Now, in the exam, guys, you would need to take that, and I would say, okay, for example, like, I don't know, I'm going to say like, okay, CT is like, whatever, t squared or so, and then you got G, which would be like, I don't know, 5 times t or something. And then you would need to take that and, you know, recalculate the whole thing. So I want to basically have the solution for that. This is going to come, okay, so let me just stress this. You're going to see that for sure, okay? But I'm going to use like simple functions and not, you know, too many complicated things. Like, you know, it's going to be very elementary because it's very confusing. It takes quite a time to address it. You understand it? Okay? So this is something you would need to basically to address. But again, you can start from here. Okay? So you don't need to develop that stuff. You can take that. I will basically provide you with that hint even. So then you would basically just need to go this far. Okay? All right? So again, it looks bad, but it's not that big of a deal. Okay, now I'm going to take it and I'm going to use it for the expression that I use for the geometric Brownian motion. The geometric Brownian motion is basically a stochastic process where these functions are constants. So both multiplicative functions inside the drift as well as inside the diffusion are going to be constants. And yeah, I'm going to take them. So that's it. Okay, so you have basically differential. First, I mean, again, so this is how it looks. Okay, I'm going to use the reparametrization now. Okay, so CT becomes mu right now, and sigma becomes G. All right, is it clear? So then this is how it's going to be. And then you can address the solution of the geometric Brownian motion directly using this formula. So you're not just basically you can use it, you should use that formula, okay? Because that will give you the solution to those equations, okay? Now, I'm going to, okay? So basically just applying it, x at point t is here, x at point 0 is here, and then e to the power of what? Now, okay, e to the power of the integral from 0 to t. First, of, in parentheses, c minus 1/2 times g squared. Now, since those are constants, as you see, so c is mu, which is a constant, minus 1/2 times g squared. Now g is actually sigma, so sigma squared, again, is going to be sigma squared. That's what you see, all right? To this expression, so this is the expression that you see here, actually. I'm not sure if this is clear. So that's why I like, using colors, because I think it's more straightforward than without. But again, not sure. Okay, so you can make your own judgment. Basically, you have the differential still, and then you have the integral, but this involves a constant. Now, regarding that one, this is interesting. I mean, you have the integral. Let me just basically take a different color. So you have the integral from 0 to t of a constant, which I call sigma, basically with the increments of a Wiener process. Now you can take out sigma from that integral, which is there, and then you have the increments of the Wiener process. Now the increments of the Wiener process between time point 0 and time point t is going to be the Wiener process at time point t again. Because at time point 0 it's going to be 0 almost surely. So I was basically just addressing that too, okay, so don't worry. But that's basically the final point, and here it is. Okay, so because sigma times the Wiener process at time point 0 minus sigma times the Wiener process at time point, the other way around. Here you had at time point t minus sigma at time point 0. This is going to be equal to 1 almost surely. Okay, so since it's equal to 1 almost surely, I mean, you just basically got those, so this is basically what you end up with. Sorry, not to 1, to 0. The Wiener process is 0 at point 0, almost surely. I'm very tired, guys, apologize. All right, so that's going to disappear, and then you have sigma times the Wiener process, which you're left with from this integral if g is a constant. You see? All right, does that make sense to you? Okay, well, and that's it. This is the solution to the geometric Brownian motion. The Black and Scholes model will thank you for it, okay? So, yeah, okay. Well, this is the stock price then. And, all right, so here you have it. Now I'm going to basically look at linear stochastic differential equations. And this is basically what it was. So this is a homogeneous linear stochastic differential equation, whereas those two functions are there, okay? And now I'm going to show you that this is true. In this case, though, I'm going to, before I do so, okay, so the previous one, I'm going to apply Ito's lemma on 1 by x. Not 1 by, I mean, not the previous one, but 1 by. So this is the inverse of it, right? So the function on which basically you apply it is basically x to the power of minus 1, which is inverting it. So I'm looking at the increments of the inverse of the function. And from now on, again, recalling Ito's lemma, which is here, so you have mu, whereas you have dt attached to it, and sigma, whereas the increments of the Wiener process are attached to it. And Ito's lemma yielded that the differential of a function of the diffusion is of this kind. Now, regarding this function here, okay, so that is going to be the function. So in this case, the function is, again, x to the power of minus 1. Then, of course, the first derivative is going to be negative 1 times x to the power of minus 2. And the second derivative is going to be 2 times x to the power of minus 3. This is it. Okay, you see? So those are the functions that I'm going to use. Again, all right? Now, so first off, I'm going to start with the derivative of 1 by x, which is, again, as I was mentioning before, negative x to the power of minus 2. Okay, so, or you can simply just write 1 by x squared, right, which is there. And then you have the differential here. So that's it. Okay, so that's, this expression is known. And then plus 1/2 times basically the second derivative. Now the second derivative is negative 2, sorry, positive 2. Positive 2 times, I forgot, x to the power of minus 3. Again, if this is it, this is the function. So this is basically the hyperbole. So you have minus 1 times x times -2, and then the first derivative and the second derivative is going to be -2 times x to the power of -3. Here you go. So that's there. Okay? And thus, this is what you end up seeing. Okay? So you have 1 by x cubed at point t, right? So let's pretend it's there. After basically it was destroyed. Sigma squared at point t, g squared at point t, g, okay, here it is. This is basically part of the diffusion. So you need to have the square of that, this expression, because that's here. Okay, so this is sigma, and then its square is going to be g squared times x squared. Okay, and that's basically what you end up with in the expression. And then, of course, you have dt, not the Wiener process, dt, due to the quadratic variation of it. Okay, and that is a reason. So what you also see, again, besides from this expression, which here comes back, the expression is not going to be stochastic, at least the expression down there. Anyways, okay, long story short, I'm going to clean this up a little bit. Here you got x squared in the numerator and x cubed in the denominator. Okay, so you can take that out, which I did. And then, of course, you could replace the differential of x by its definition, which is there. It's not that big of a deal. And then, of course, okay, you can clean it up again because you got x squared in the denominator and then you got x in the numerator. So that cancels itself. You got x by 1 by x, which is, okay, for me, that was fine. Okay, so not that big of a deal. But as you see, it looks more, let's say, compact in that regard. Okay, and then on what you can do is, I mean, again, you can take that and put it in here, into that differential. You're going to see this. Okay, so it's here. Okay, first off, I'm going to get rid of the negative sign. So I'm going to multiply all my summands by -1, which I did. And then, of course, inside that, you can, since dt is also here, this expression can also come with it. So this comes actually into the, I mean, as you see, I mean, you got 1 by x over here already, so this is not something where you need. And that's it, okay? So that looks more compact. Okay, now this will help me to actually to prove the second part. I'm going to just use it, okay? But these are things that you would need to do. Ito's lemma, actually. So we were practicing Ito's lemma right there. That was part from last week's lecture, but you're going to need it here. All right, now, how to go on? Integration. I mean, you could go on and you would integrate the function so that you could find 1 by x, which might be important, right? Which can be a function of it. Okay, so, but now not this one, not this time. Anyways, what I'm going to do is going to apply the stochastic version of the product rule, and I want to recall it. You might remember it. Okay, so there is going to be a stochastic version. The reason is why I basically need to write it like that, because in terms of differentials is that these functions are not differentiable. All right, so neither x nor x1 nor x2 is going to be differentiable. However, you can generalize basically that notion, okay, because they're not differentiable, but they're Riemann integrable, or they're integrable, let's say. We'll just call it integrable, which is a weaker condition than being differentiable. Puts much more restrictions on a function. All right? Okay, so for example, the density of the uniform distribution is, the continuous uniform distribution is not differentiable, at least not almost. Not everywhere, but it's going to be integrable. Anyways, okay, now you get a Wiener process, and then of course you want to basically address the differential of the product of the two, okay, which you would, meaning that you would need to look at the increments of the product. What's happening? All right? Anyways, okay, so that could be just two processes. Anyway, I was explaining that already, so I'm not going to do it again. Everything seems fine. I thought I would make a mistake. Sigma 1 is the diffusion of the first, as you see that from the index, and sigma 2 is the diffusion of the second. And again, this expression is not there when you do derivative calculus, of course, right? But since the Wiener process has a quadratic variation which is finite and not zero, which is positive, okay, then you need to basically consider that expression as well. Okay, so now what I'm going to do, okay, I'm going to rearrange this a little bit so it looks nicer, because the expressions that I'm going to insert here are quite big, okay? So I'm going to write those things a little bit more structured way. And yeah, so then I will apply this on, again, so this is the rule. I will apply this, whereas a second diffusion is the inverse 1 by z, which z was also a diffusion, okay? So x and z are not the same. Z was the auxiliary solution to the homogeneous solution, right? That was a homogeneous solution, okay, for the homogeneous process. You might not understand this, but maybe you remember that I was basically addressing the differential of the quotient. And I like the stochastic product rule better than the quotient rule, because the quotient rule is giving me, like, I don't know, bad vibes or something. There was too many, you know, second derivatives and whatnot. No, none of that stuff, right? So I was basically just using that one. Anyways, okay, so long story short, now I would replace the second stochastic process by 1 by z, which I did, including its differential. So you can see there is basically, that was 1 by z is now, or was x2 even. And I'm going to index the diffusions basically completely new. Okay, so one is x and the other one is 1 by z again. All right, so which is basically here in this case. All right, so these are the expressions that are involved. And now I'm going to prove, not that, because this had been more or less explained last week, but I'm going to basically show you that the solution of an inhomogeneous linear differential equation, stochastic version, how it works. Okay, so first off, I'm gonna take care of that differential dx, which is a diffusion, right? That was a diffusion. Here, check this one out. I was basically addressing this already. This was, again, so you have a inhomogeneous stochastic differential equation, okay, by which I'm going to replace the differential of diffusion with, actually, this is its definition by now. So this is where you would starting it, okay? So that's the biggest one. You understand that? Okay, so I'm going to replace this expression by that, or basically the former xt, sorry, basically in this expression, okay? So I'm going to take that, here you have it, and substitute by it so you see, okay? Just that. Again, it's very big, so if you don't get lost, then congratulations. The diffusion is here. Okay, so this is the diffusion of that function, you see? So you can simply just replace it by it, okay, which I did, okay? And I'm addressing basically the differential here, that one, okay, which I don't know. So here it is. And I did it before in a little exercise with Ido's lemma. Might remember that, okay? So that's the price that I was paying. So that was, the result was 1 by z. Times, and there is another function, g1 squared at point t minus c1. This is the first expression, and then you have basically the second one, g1t, where this is attached to the increments of the Wiener process. g1 is the multiplicative function for the diffusion, okay? And g2 was the other, but I don't see it anywhere. It's here, it's somewhere. Anyways. Okay, so I'm going to replace the other diffusion by that with, okay, because again, that was the reason why I was preparing it. Okay, I'm going to clean up this mess, so don't worry, it's not going to be that big of a deal. Again, it's not difficult. You know, just you need to work a little structure, you know, you're looking at the structure. So watching it is basically, as it turns out to be the case, not difficult. Now, this is going to be the diffusion of the process 1 by z. And that was basically the differential of it. And here is its diffusion, or basically it is also attached by the process itself. So this is going to be 1 by z minus g1 by 1 by z. This is basically what the diffusion of that is going to be. And I'm going to write it like this. So as you see, okay, minus g1 times 1 by z is the diffusion of that. And this is basically attached to it. So here you have it. This is it. This is it. Okay. I was inserting everything I got. Okay. And now I'm going to clean it up. Now, you might see a little bit carefully because what you got here is this. I'm not going to read the indices, guys. So I'm not going to read the t's now. Okay. Because those things distract me. X by z times negative C1. Keep that in mind. Okay. And here at the top you got, I mean, you could reverse it, X times C1 by Z. That's the same thing. And here you have minus, right? So they're going to be killing themselves, right? Okay, so you can take those out, which I did, okay? Why didn't that disappear? Because there is also other expressions that you need to multiply that with, so I'm not supposed to just take that out. Okay, but where it's gone, it's gone. All right, so then it's going to be more compact then. Now those expressions are also there. These are the increments, include the Wiener process, okay? Here you got g1 times x, which is here g1 times x. And then all things are multiplied by 1 by z, which is here. And then, of course, you have a minus sign. So the minus sign allows you to get rid of those, which I did, okay? And I'm going to I was taking those out. Now, you might ask yourself, okay, how come that the Wiener process is still in? Because you got one expression here that is also multiplied by it. So it's not a multiplication, but let's say a pseudo multiplication. So it's still there, okay? Now I'm going to take care of those two because that's also actually the case here. I mean, okay, that's the first one. That's going to be the second one. So this is going to be g1 squared times x by z. And that's going to be seen here. g1 squared times x times 1 by z, or by z. It's the same thing. Okay? So I'm going to get rid of those two. Okay, again, so you might feel kind of like, okay, overrun, and I understand that, but I was just cleaning this mess up. And cleaning up is something I like, okay? So again when I do mathematics at least, you know, so again, it's becoming very easy. I mean, compared to the expression that you saw, okay, relatively speaking, of course. So it looks much more humane now, okay? And now you can integrate. And how would you integrate now? Okay, because you got the differential here. So you can practice it, guys, now. Okay, how would you integrate? You got x at point t by z at point t minus x at point 0 by z at point 0 equals, and then the integral part of this equation now, or on the right-hand side of the equation above, which is given by the differential notation. Okay? So I was doing that here, but yeah, okay. And I put basically the starting value of that quotient to the right-hand side already. So that was on the left-hand side, now it's on the right-hand side. And then plus, I mean, the integral of the rest. Okay? The reason I was basically writing like this slowly is you got 1 by z, which is a factor now, and this is going to appear in the denominator of the integrand of that expression. Okay, you see? Again, it looks horrible, but all you would need to do is just to clean it up a little bit. Again, you need to multiply this expression by that, and then you're going to get a fraction. And you integrate that fraction, and I'm changing basically the integrator from t to s, such that basically the upper limit of that integral can be equal to t then, okay? And yeah, I'm going to do the same thing here for the other. Okay, this is a quotient which you will have, but you got g, all right, divided by z. That's it. And that's basically the expression that you would need to integrate. This is s. I apologize. I just saw it. Probably it's wrong on the slide. I got so many s, t's, d's, whatever. I was like, you know, I'm running out of constants, man. So I need vocabulary. Okay, this is S if you recognize that one. And yeah, you would need to take the integral of the other. G2 by Z, which is there. All right? And yeah, so then of course you're left with the increments of the Wiener process. And if you solve this equation for x, which you would need to multiply by z on both sides. Keep in mind that z at point 0 is still equal to 1. So this denominator on the right-hand side, so you multiply the starting value and this integral by z. And z, I was giving you that already. I'm writing it down again, is here. Okay? Again, I apologize. The integrator of the integral of the middle is wrong. But here it's right. Okay? So this was it. That was the big expression. That was a solution of the homogeneous counterpart, whereas you would have the starting value multiplied that way. So, but that was it. Okay? You understand this, guys? Okay, so it's not difficult, to be honest. Again, don't take that with a grain of salt. I want you to basically feel encouraged by it and not frustrated by it. Okay, so again, just because a lecturer says it's easy, it doesn't necessarily imply that it is, but practicing it would make the difference. Okay? All right. Now I'm going to apply this on a specific example. So that's right. Okay, so you start from here, getting the solution of the stochastic process, okay, which again is here. So that's it. Okay. And yeah, okay, so let's do it. Okay, here is the example. So regarding, for example, the general Ornstein-Uhlenbeck process. You might remember that one. I'm not sure. If you don't, that basically you can check it out, but this is going to be a special case of this process. Okay? You're going to have an additive constant and a multiplicative constant, but only for the drift function, not for the diffusion. The diffusion is always going to be basically only depending on the additive constant, as far as basically the general version is concerned. Anyway, so I'm going to show you what it was. Okay, so let's say you got a constant which I call C1 now, okay, which is a multiplicative one, and then you got the additive one. This is it. And then you got sigma, which is just the additive constant here. You see? That one. This is gone, okay, because then after that, the Wiener process comes. And that's it. Okay, so that's basically differential notation. Okay, all right. So, okay, now let me find z first. This is where you begin, because that's the auxiliary function that you need to multiply the starting value with, and then the other integrals, and I'm going to need them here. You know, so that's basically what I do now. Okay, so how to solve basically that differential equation for yielding the Ornstein-Uhlenbeck process. Now, first off, again, just focus on this, basically on this row here. Okay, so the final one. This is e to the power of, and then you have the integral from 0 to t of a constant. You see, C1 is a constant now. This becomes here C1 minus 1/2 times g squared. Now, g1 squared here is sigma, right? Okay, sigma is the, no, that's not. 0, that's going to be 0. That's going to disappear. Okay, that's not there anymore. Maybe I did a mistake. No, thank God, that was 0, right? This is the multiplicative constant, it's there. It's not there, okay? Because then you would see basically the process itself in, basically inside the diffusion, which is not, okay? Now, okay. And then continuing, all right, so you have the integral from 0 to t. G1 is 0. Okay, thank God, so you're going to get rid of a lot of things, obviously. Okay? Actually, the only thing remains here, when you look carefully, now this integral will disappear. I think everybody sees that, right? Now what about that one? Again, this disappears in the middle, and then of course the parentheses do. So then inside the exponent, you got a constant. So e to the power of basically an integral of a constant. Now the antiderivative of a constant is going to be a linear function, of course, and that goes from 0 to t without an intercept. This is going to be just c1 times t after all. Okay? We did that, so this is basically what it is. Okay? So I was calculating that, and then I'm going to basically put it together. So let's say this is a typical example, and I would like you to ask you to do it just the way that I do right now. Or not right, but I do it now, so then you do it after that. Okay, you got the process at time point t, okay, by multiplying the starting value as well as, let me underline here, the starting value as well as this integral by z, and that's going to be it, right? Nothing special. Okay, I'm going to write it down. So z is here, this is z, and I'm going to take care of the others. Minus, again, so this is starting value from the integral from 0 to t of c2 by, and I was basically just pulling this off, okay? So g2 is 0, right? What about g1? Or minus g1, okay, you're gonna see that later on, okay? So I was basically addressing that. No, I mean, okay, if this is 0, then this is going to disappear as well. Okay, so you got just that. Sorry, I didn't see it. Now I do. And then there is the other integral with the increments of the Wiener process. You got G2, and G2 is the additive constant, which is sigma then. Okay, I'm not sure if you're seeing that. Wait a moment. Let me underline this better. Here is sigma. Here is G2. And yeah, which again demonstrates the coordinates, and then you got G2 in the numerator, which is sigma then. Okay, so for the next one. So integrate from 0 to t, and then you got sigma. Divided by e to the power of now what? Okay, I mean, again, so you have the function z is over here. You need to divide it by e to the power of z at point s. So you replace t by s now. Okay, e to the power of c1 times s in the denominator, and then you integrate that with respect to the increments of the Wiener process. That's it. Okay, now we clean up a little bit. Okay, because I was addressing the antiderivatives actually of those functions. Again, especially that one. So that was a function that I wanted to ask you to remember. Negative c2 by c1 times 1 by the exponential function at point c1 times t, and that's it. Okay, and then we, of course, you got minus 1 inside the brackets, but that's just another thing. Okay, and that's it. That's it. Okay, we don't go further. Okay, so for that Riemann-Stieltjes integral, you don't need to go further. Why would you? Okay, now, believe it or not, this equation solves this stochastic differential equation, or this function, right? So that's a solution to that. Okay, so the application is as follows. So when you try to describe dynamics of a series, for example, in a more sophisticated way, then you could basically just use differential equations by doing so, and then you would need to solve them, basically getting the process itself, which, have to be honest, can look complicated, actually, all right? Okay, now keep in mind, guys, the only stochastic component here is the integrand of this integral. Okay, everything else is deterministic by now. Okay, so it's not that bad. Okay, and then I'm going to address the standard version. Where for the standard version, you take out the additive constant inside the diffusion. You are allowed to do so, which I did, if this is 0. Okay? So if that is 0, the whole thing becomes 0. Guys, if you multiply a fraction by 0, you're going to get 0 back. I think that should be clear now. Right? Okay, I hope it basically demonstrates, I mean, this is it. Okay, so that thing will disappear. And yeah, okay, so here, and then you end up with this expression. which again I was collecting here, which is much more compact, much more. Okay, you see it? All right, so all right, here we go. Yeah, let's have a look at the following statement. So we're going to look at the moments, and that's going to be the final part, so it's not going to be that long. The moments, the expectation, as well as the second moment of the solutions, and yeah, for the stochastic versions. And I'm going to start basically by the general expression, so it's not a big deal. And then, of course, you can take every other case as well. Okay, so here both you have an additive as well as a multiplicative function for the drift as well as the diffusion. And let me check. Seems it works. Okay, well, all right. And okay, and then of course you have actually basically, I mean, for the C's are for, I mean, the additive and the multiplicative functions for the drift, and the G's are the additive and the multiplicative functions of the diffusion. And the question is, okay, how would you get the first moment? And I'm going to basically prove those statements, and but not going to address an example. So I would like you to look at an example, at least for the geometric Brownian motion. Okay. Now, regarding the first moment, which is simply just expectation, it's still a lot of work to do. I mean, you got a function which is z1, okay, because there is going to be two of them, z1 and z2. So z1 will be basically the auxiliary function for the moment here. This is not going to be a process now because you have an expectation operator here. So it's going to be a deterministic function, all right? Okay. And that will resemble basically to the structure for stochastic differential equations that are homogeneous. So you got the expectation of the starting value, which again resembles to, I mean, so it has the same structure. And then you have this integral from 0 to t of C2, which is the additive constant, and then you have Z1 there, which I'm going to define below. Okay, so if, let's say, there is no additive, not constant, sorry, no additive function here, the diffusion, then this integral will be 0. If there is, then you will need to take care of that. For example, for the Ornstein-Uhlenbach process, there is one, but for the geometric Brownian motion, there is none. Okay. Now, and then, of course, you got Z1, which kind of resembles to the functions that you saw. Okay, so you have just the multiplicative function that you would need to integrate from 0 to t as an exponent, and that's pretty much it. Okay, so that's not that bad. Okay, just to say that. All right. Anyway, okay, so here it is, and after that you will need to address basically also the second moment. Now the second moment is painful, okay, and then you would need to calculate maybe the variance even. The second moment, you have another auxiliary function z2, which is on its way. It's going to be the same structure, but it has more auxiliary functions, and I would change the auxiliary functions to gamma. So this is a letter gamma. This is a Greek letter, actually written like this, but for this editor, I use it. It kind of look like Y, but it's gamma. Auxiliary functions. So structurally, it's going to be the same. Gamma 2, and there is going to be gamma 1. Gamma 1 is going to be here. So that is a function that you would need to integrate. And this is 2 times C1 plus G1 squared, right? That is gamma 1. Why? I'm going to explain this later on. And gamma 2 is a big one, okay? So that is a, little work to do. So you have the additive constant, then you have 2 times G1, which is the multiplicative constant of the diffusion, multiplicative function of the diffusion. I was thinking about the geometric Brownian motion, by the way. And then you have also the additive function, okay, which is also there. And that is multiplied by the expectation of the starting value, expectation of t, not the starting value of t. This is the function at point t. And then there is also an additive constant here, or additive function here, which is g2 by the way squared. Okay, sometimes I cannot really always recall it myself, but this is a big one. So, and then you would need to still divide it by z, right? And then you would integrate it. So I did it for the general Ornstein-Uhlenbeck process. Of course, I would need to stress that this is going to go way beyond the exam, but I did it, okay? So, but you don't need to. And you find this in the solution, but maybe you could still do it. Even there are constants. Okay, so even though these things are constants, you would realize that it's still quite painful sometimes. Anyway, and then you got the expectation even there, right? So this has to be integrated even, because that is also a function of t, okay? And that's not going to disappear. All right. Anyways, yeah, so, well, okay, I'm going to prove it for both, for the second and for the first moment. And please try to actually to remember the techniques that I used for the first moment, so then you would understand that, because I'll skip those for the second. Because for the second moment, I'm going to do 3 steps in one, okay, to make it a little bit more shorter even, okay? First off, I'm going to integrate the process here, okay? That's step number 1. Step number 2, then I'm going to apply Fubini's theorem. You might remember. Fubini's theorem allows me to bypass the expectation operator by the integrals. I'm not sure if you remember that, but the expectation of, let's say, all right, so of an integral where there is, or there was some process, right? Okay, is or was simply just the integral of the expectation of the process. Okay, that was Fubini. You might remember that one. Okay, so you can bypass the integral by the expectation. Let's assume that this is going to be the case. I mean, you would need to check first, but I didn't, so that was too much. Okay. Then, so again, first off, you integrate the process so that you could do it, because then you have integrals that you can bypass. Second, you apply Fubini's theorem. And third, you will differentiate again. And these are the 3 steps, and I would like to remind you what happens to that if you do it. Okay, so keep that in mind when you basically are doing it. Okay, so first off, I'm going to integrate the process. Again, how? You can simply just need to remember, you simply just put on an integral basically on those processes, and focusing on that, the first integral is x at point t minus x at point 0. That's the first one, okay? Because you sum up the increments, and then you basically start the end point minus the process at the starting point, and that's basically the total change, right? Again, so not the absolute change, but the total change. All right, so this is it, okay? And then you put it basically to the other side. So you have basically the starting value on the right. And then you can simply just, get it. And then, of course, you have the rest. So here is the diffusion. You have the integral of that. Okay, so I'm just simply writing it down. And then you would integrate that from 0 to t, which is going to be here. So you take that. Of course, I will change the integrator, so which I haven't in one slide, but I will fix that one. Here in this case, I was changing it to s, and then of course I would need to integrate from 0 to t the other, where I would do the same thing. Okay, so that's basically just going from the differential operator to the integral, from differentials to integrals and vice versa. You could basically go the other way around. Okay, the reason why I was doing that is because I cannot bypass by the expectation operator. I cannot apply that on differentials directly. So the differential of the expectation is not going to be the expectation of the differential. It doesn't really make sense because the differential does not exist. This is just actually a notation, by the way, representing some increments that were infinite, and the time steps are infinitely small. Anyway, but I can basically address the expectation. And by doing so, I'm going to basically apply Fubini's theorem. So before I apply it, just to note, quick note, the expectation on the left-hand side is going to be the expectation on the right. That's the point. And the expectation of a sum is going to be the sum of the expectations. So the expectation of the left-hand side equals the expectation of the starting value plus the expectation of the integrals. And by doing Fubini, the expectation of the integrals will be the integrals of the expectations. Just that. You might remember that. Except for the latter, because this is, you might remember that, this is a Riemann-Stieltjes integral. And the expectation of a Riemann-Stieltjes integral is, you might remember that one, 0. So for that, I don't need Fubinis to apply. Okay? So the expectation of that is going to be 0. So that will disappear. You understand the point? Check it out. That was a Riemann-Stieltjes integral. Go back again and have a look. Okay? All right. So, and I did it here. So this is the expectation on the left-hand side, the expectation on the right, and now I'm breaking in. Okay? Because Fubini's theorem allows me to do it. Expectation of the integral is then the integral of the expectation, provided that the function is absolutely integral, which I assume to be the case. Okay? And what about that? Now here you don't need to have the expectation because that is going to be, this integral is going to be 0. You understand the point? Again, so then you could not break in. You could not break in if basically you have a Riemann-Stieltjes integral. In order to get basically the expectation of that, you have to apply integration by parts. Within that, and that's going to be also relevant. So stochastic integrals are going to be definitely common. You're going to see Ito's lemma common, and then of course based on that, stochastic differential equations. Okay, so these are at least half of the exam. Other half, I need to rethink myself anyway. But that's it, okay? And then it's going to disappear now. So now the question is, what about that? Now for sure, I'm going to address it just simply by just basically differentiating again. So now we're going to get back, and I want you to check what happens to the expression after that. Okay? Now this is going to be the expectation. The differential of the expectation. Now, you subtract the two, the expectation at the endpoint and the expectation at the starting value. Subtract the two, and then you're differentiating it, and that's what you're going to get because that would be the integral afterwards. And in order to do so, you simply you need to get rid of the integral, and that's what you end up with the right-hand side. Okay? So that's basically what you had done, and this is basically what happened. And I would like you to basically mind you on that. You were calculating the expectation of that the differential of that expectation of the process, and all you would need to do is just to replace the process by its expectation after all. And that's it. So that's basically it. And guys, this is a deterministic differential equation, which is inhomogeneous. And we were addressing its solution already. And that will be solving it for the expectation. You understand the trick? So what you see here is a deterministic differential equation, DDE, right? For which I was showing you how to solve it, which I did, and that's the proof, all right? And that's it, okay, which is not a homogeneous one. Okay, so solving this inhomogeneous DDA is actually yielding the result, which I did with the z's and all that stuff and the starting value. You might remember that one, okay? Here is the expectation of the starting value, and then plus, this integral, okay? And this is check this out, this is the additive function, and then you got z basically in the denominator, okay? And then of course you would need to address z as well, okay? So which is e to the power of the integral from 0 to t of the multiplicative function with respect to s, all right? So since this is, this is what it actually evolved from here. Okay, so from this expression. All right? And that's it. That's it. This is it. Nothing more. Okay? Now the variance is not so easy, because thank God the expectation of the Riemann-Stieltjes integral is 0, or was 0, or the variance or the second moment is not. Okay? And that is a point, and that's basically what you will need to consider when you deal with that. And there is also basically the quadratic variation of the Wiener process, but I'm going to show you basically what is happening there. Okay? So now I'm going to basically look at the second moment. So these are the things that I would basically, you have the expectation operator breaking in. Now, before you do the second moment, I want you to do Ito's lemma again. We would do Ito's lemma for the parabola. Okay? So when you have basically the parabola, okay, the first derivative is going to be 2x with respect to x, and its second derivative is going to be 2. Okay, so keep that in mind when you basically deal with that, because you will need to have that for Ito's lemma after all. I will give you Ito's lemma again, so you'll see basically down there when it's coming to that diffusion, the differential of the function, which is the square now, and then you would need to take the expectation of it, and then you could take it out. So basically this is what it's going to be. First, I would need to have the derivative of the square, which is 2x now. So everybody knows basically what the derivative of parabola is. And then plus 1/2 the second derivative times the square of the diffusion. And then of course you have the differential basically with time. Okay, so that's it. That's also not that bad. Okay, well, okay, we're going to apply this. So this is going to be 2 times x basically, right? You see, 2 times x dx, which is basically giving you the diffusion. But again, here it is. So I'm going to replace it by it, and then you'll have plus 1/2 times the second derivative, which is a constant now. Okay, so that's basically what you'll have, which is 2. That was 2. You might remember that. Derivative of 2x was 2. And then the square of the diffusion. The diffusion is here. So then you would need to square it simply, which I did. So I was collecting it. So I was, you have those brackets, and then you take the square of it, and then you put the diffusion in there, and that's it. All right? And then you have dt, not the increments of the Wiener process, dt, which is basically the differentials here, or the increments of time, you can say, where basically those increments are infinitely small. All right? Now, this is more difficult than you might think, because, again, what you would need to do is now you would need to replace the diffusion by this big expression, and then cleaning this up is like, kind of shaky, but again, we can do it, so don't worry about it. Anyways, okay, this expression comes basically from the fact that the quadratic variation of the Wiener process is finite. Okay, if that was 0, then you would not see it actually. Anyways, okay, I don't need to say that 1/2 times 2 is equal to 1, so I'll take it out. And now I'm going to replace it by the big expression there, which is, also, just a moment, let me check. Everything works fine. All right. Okay, here it is. Oh, it closed. God damn it. I will cut this off. It turned itself off. I hate this. It was too much for it. Too difficult for the presentation. It was a second moment, right? We're right there, just at the end. Yeah, okay. Let me start from here again, because, again, unfortunately, I was not able to identify which slide that was. It turned itself off. And yeah, here it is. Okay, now let me go back. Here it was. Okay, I apologize. All right, so yeah, okay, now we need to clean this up, and it looks horrible as I have to admit. Something like this again, I'm not sure even if I would be able to do it without the colors, to be honest. Okay, so first off, what I did is basically putting, taking the square of that, using the binomial formula. I mean, let's do it here right there so you can see basically what it's going to be. This is going to be g1 squared times x squared plus 2 times g1 times x plus g2 squared, right? 2 times g1 x g2. I forgot g2. There you go. Okay, so that's it. Okay, here it is. G1 squared, if I recall it correctly, times x squared plus 2 times g1 times x times g2. Okay, I put g2 to the front. And then I got g2 squared. There you go. Okay, and that makes it even worse, but it is what it is. I will need to clean it up. Don't worry, I help you out. First off, this is the only expression where the increments of the Wiener process is. Okay, so then you would just, put that aside, and everything else can be cleaned up without it. So I would take those. Okay, now there is expressions that are basically, first off, I multiply 2x by this expression. So you got 2x times c1 times x yields 2x squared c1. This is becoming it. And then you got 2x times c2, which is 2x times c2. So that's what you're about to see. Okay. And okay, now everything is ready. So now what I'm going to do is I'm going to do some grouping. These are the squares of x. Okay, then I will need to collect. And x squared times 2 times c plus g1 squared. Keep that in mind. So I'm going to regroup those, okay, because I want to connect them. Here I got the x's, okay. So x times, in brackets, 2 times c2 plus 2 times g1, g2. All right? And then the final one is here. This is the final one. Okay, the blue one. So those are the 3 groups. Okay, this is not a group, but anyway, okay? And I'm going to regroup them. So you're going to see the green ones elsewhere. I'm going to change the 2. That's it. So then, of course, and I will basically connect them, okay? And that's the only thing that I do. So again, changing those 2. Or swapping. I'm not changing them. I'm swapping them. Okay, and that's what you're about to see. Check this out, because I can only show it once. Here it is. Okay, let me go back. Here it is. You see? Okay, again, this is just as if I was rewriting it then. But then it's not that difficult. So just rearranging these issues, I mean, it's not that bad. Okay, so you got x squared times this thing, and then plus x times this thing. Okay. You got some x squares down here, but these things will, if you put basically first an integral and then the expectation operator on it, you find that this is going to be 0. Because this is going to turn to a Riemann-Stieltjes integral. Okay, you have the increments of the Wiener process. And the expectation of a Riemann-Stieltjes integral is always going to be 0, even if you got the squares in here. Okay, so that's, thank God, at least I get rid of those. Okay, so I'm going to get rid of those expressions. Those will disappear. Okay, they will, but the others don't, unfortunately. Okay, and I cannot isolate that directly, so you will need to make up your mind later on. Okay, but I'm going to do basically integration, Fubini, and differentiation at the same time. So then I'm going to put basically the expectation operator bypassing the differentials, which is mathematically not clean. all right? But it works, okay? Thank God. So this is basically what would happen. So what I'm saying is this. For the first differential, I'm going to put the expectation operator on it, bypassing the differential. So you have the differential of the expectation. This yields the expectation of x squared, and everything else will be the same. And then you have the expectation of x. And this disappears because this will be, or would have been, actually a Riemann-Stieltjes integral, a stochastic Riemann-Stieltjes integral, which has the expectation 0. You might remember that. So we will not need to bypass that one. But I did. Okay? So then I did 3 steps in basically at the same time. Okay? But mathematically it's not very clear. But this is what happened in the first step, so why would I basically redo it in the second? I was just basically making a shortcut. But again, I have to admit, from a mathematical perspective, it's not very clean, but it worked, and it is correct. So this is basically it. And now you have a deterministic deterministic differential equation. Okay, if you're not seeing it, I'm going to show you. So we are going to define 2 functions, both depending on t. The first one is going to be here, this expression, as you see. Well, okay, as if you would multiply that by that function. And the second expression is going to be here. This is it, okay? But that's a big one. And the most difficult part is going to be the expectation of that, you see? And this needs to be incorporated into the formula because these are just the building blocks of it, okay? So that's a huge deal, okay? As you see, it's a huge deal. Okay, but there is no shortcut, no way around it. You cannot get rid of it. It's just like a cheap suit. You cannot get rid of it. You understand the point? Okay, and these are the blocks. Okay, so if you put that back, right, as you defined it, you realize that you have actually a DDE in front of you, a deterministic differential equation with these blocks. Okay? Which are called gamma. Gamma 1 is the multiplicative one, and gamma 2 is the additive one. Okay? And they are big. And again, so the basic problem is here, the expectation. Okay? You would need to integrate that out. But again, I did it with the Ornstein-Uhlenbeck process, and it took me an hour. Last night I was... it took me an hour, so I was going crazy. It was like 3 or 4 a.m. I cannot recall. Anyway, but I wanted to have that done. So you don't need to do this. Okay, so if you want to get a hint, basically, I'm probably not going to address the second moments. Maybe it's just a very basic one. Okay, so don't take that with a grain of salt. So when it comes to the second moment of the solutions of differential equations, or stochastic differential equations, only if it's very easy, basic, okay? Not the big ones. Like, even if the Ornstein-Uhlenbeck process was just like, yeah, it gave me headaches, all right? So that's pretty much it, okay? But you should try at least for the geometric Brownian motion. So that is part of the last exercise, but you should do that for the geometric Brownian motion, and you should get at least the expectation of the Ornstein-Uhlenbeck process, but not the second moment. That's a big one. This is I was getting crazy, you know, so, but that's pretty much it, okay? Now, regarding the exam, I will keep you posted in the group, okay? I will basically create the exam tomorrow, and after that, yeah, actually I will try to submit, and yeah, see what you end up with. But Ito's lemma is going to play a huge role. You're going to have stochastic integrals, you know, all 3 types, you know, the Riemann-Stieltjes in the Ito type. The Stratonovich, not that one. So this is just maybe like a hint or so, but have a look. And basically on the exercises. for the Ito integral, you start at the lower end point of the partition. And I was also solving another one where you would start at the upper end point of the partition and showing you the difference between the two. So check that out. What else? Okay, so integrals, Ito's lemma, and that type, and the rest, I will basically give you the rest, but you know, the convergence type, like maybe, you know, you should know the random walk and all that stuff. So, but it's very difficult for me to assess. It's more like theoretical. So I will take my exercises to basically for inspiration, okay? So, but maybe like a short version. It's not the crazy ones, okay? So not the ones, but these are the things that you would need to deal with. And you should basically also be good at, let's say, relatively basic integral and differential calculus, okay? But I won't be that crazy regarding it. So if the antiderivative is not straightforward, I will give it to you. So then you can skip integration by parts and things like that. All right? Okay, but not for the formulas that I applied. So if it's in the script or you saw it on my slide, that you could basically make sure that you have that ready. Okay? Okay, so whatever formulas you see on the slide, you would not need to show it again. Okay? So that's not the point. Okay, and I will give you further information because I have, to be honest, I have no idea what to do. So, but you're gonna see something like this. So again, take the last exercise 8, exercise 9, exercise 7. These are very important ones. Stochastic integrals, random walk, stuff like that. Okay, that's for sure. And the theoretical ones like the sigma algebras, and not so much. Okay, so at the beginning, like when I was introduced you to random variables, but again, I will be more specific in the group, so check out the messages maybe every other day. And I'm going to host a Q&A, so 2 days prior, probably Monday. Is that all right, Monday? So I could take questions, and online, of course, so you don't need to come. And so then you have a day left when you can prep. And so, okay, 6 o'clock, 7 o'clock, 6 o'clock will be fun. Monday, 6 o'clock, 6 p.m. Not in the morning. I mean, you can have it in the morning, but. All right, guys. Yeah, so I'm not, but just to be honest, I'm not going to ruin your career. Okay, so take that as a promise. Okay, so I don't go beyond the exercises, if that's answering your question regarding the difficulty. Anyways, guys, okay, yeah, I will take questions. Check out my posts in the group, and yeah, and I will be there, so I will be hosting the exam, and yeah, see you then. Okay, take care.